Yikes. All right, well, we're recording for like the last 20 minutes now, everybody. Sorry about that. Thank you, Devashmita, for saying that. You didn't have to say that privately, though. Just come out and shout at me. Somebody at the beginning of class next time just needs to shout at me to record. I'm going to punch myself every single time if I don't do that. Okay, let's look at these other questions. Would it be possible to talk about what quasi-static means again? Yeah, so let's go back to quasi-static. So quasi-static was basically just we are applying some kind of compression such that we're at equilibrium at every single point along the way. Whether or not adiabatic compressions can be quasi-static. Yeah, I guess I addressed that early on. Book put quasi-static next to the work formula integral. Is the book setting some limit on this formula? Does it have exceptions in certain adiabatic processes? No. So every single time we assume a process to be adiabatic, we're also going to assume quasi-static. Quasi-static will always be assumed unless we explicitly say otherwise. That's going to be a fundamental underlying assumption to make our lives significantly easier. Okay, so yeah, I apologize for that. I need to pay more attention to the chat. I need to pay more attention to actually recording. Hopefully that doesn't inconvenience too many people. So yeah, we just wrote down what the specific heat at constant volume is for a system that obeys the equipetition result. Now let's look at CP. So the heat capacity at constant pressure. So if it's an ideal gas again, and we've got this result, then we can take our expression that we just had before. We had du dt, the constant pressure, was the first term right here in our heat at constant pressure. So let's just look at that in particular. So if we put that guy in, we can actually show that it is the same thing as it is for the constant volume case. So those two pieces are exactly the same. And the second term can be calculated. Since we have an ideal gas, we have PV equals NKT. So we have that V is equal to NKT over P. So in that case, if we look at the second term, it looked like this. It looked like P times del V del T at constant pressure. Well, we can write that exactly. So let's do that. So we would get P times NK over P. So the P's cancel out. You just get N times K, or likewise NR. So this is the number of particles in the Boltzmann constant. This is the number of moles in the ideal gas constant. So in general, we can write for the ideal gas is a relationship between Cp and Cv. We can write Cp is Cv plus Nk, or we can write Cv plus Nr. All right, we are just about through, so just bear with me. One other topic that I want to address is what's called latent heat. Talked about this very briefly before. Okay, so yeah, we mentioned before that all the energy of the system when we were calculating it with like the gas in the cylinder was all going into kinetic energy. But in reality, some energy is also going to exist in chemical bonds of the gas, and those things determine the state of the gas that we're talking about. Or it could be a liquid, a solid, Bose-Einstein condensate, whatever. So let's see. So this is basically energy that's going into the system that's not changing temperature. In or out. So if you think of like, let's just say your model of like your liquid or something is basically just like 2 point particles with some bond between them. As you heat up a system of these particles, like they bounce around faster and faster and faster, but then at some point, energy goes into actually severing this bond right here, and they move out of their liquid state and they turn into a gas. So the energy that's going in to actually break that bond right there is not changing the temperature of the liquid. It is simply changing the phase. So yeah, this occurs at phase transformations. So does anybody have any examples of phase transformations that they think? Right off the top of your head? Yep, boiling, water. Anything else? Melting, ice. You also melt iron. Could cool something until it's a Bose-Einstein condensate. Good luck. And so technically, the defining feature of these points is the following. What is a Bose-Einstein condensate? Go on Wikipedia and read about it yourself, but it's a very, very special state of matter that only exists when you get something really, really cold. And so the way that you actually typically produce these things in the lab, to my understanding, is you use so-called like magnetic cooling. So it gets to the point where you can't get heat out effectively through like any kind of like heat pumps. So you literally make like an electromagnetic trap. So like you've got, this is a bit of an aside. You've got a bunch of particles left over and you've got some kind of trap, and you lower the energy requirements on this trap such that the higher energy particles, they bounce out every single time you lower this trap, and you just keep on lowering it and lowering it and lowering it until all you're left with are things that are at a really, really, really low temperature. And there's a discrete transformation here in going from some number of particles to some fewer number of particles that people refer to as a Bose-Einstein condensate. I don't know if we'll actually cover that in any detail in this class, but it's very interesting. So yeah, the defining feature of phase transformations is that since we have C equal to Q over delta T, well, it's specifically a point of discontinuity. Yeah, it is crazy. It's a discontinuity here because you have a point where you're adding in heat, but the temperature isn't changing. So it's a discontinuity in the heat capacity because it just blows up at that point, right? So that's actually like the mathematically defining feature of phase transformations. Okay, let's define exactly what latent heat is now. So latent heat we'll refer to by a capital L, and it is just defined as the heat over the mass. And here the heat, it just refers to the heat that you have to either put in or take out in order to accomplish the transformation. Whatever transformation it is. Yeah, and again, Q, the heat, is ambiguous because there could also be work being done, but by convention, P is constant, and the only work that's being done is by expansion and compression. So not a whole lot more to say about this right here. We could look at maybe some specific latent heats. So in order to melt ice, for example, and we're getting close to being done. I know we've only got 1 minute left, but I've only got like a half a page to cover as well. So just bear with me. So melting ice, it's about 333 joules per gram in order to accomplish. Boiling water is 2,260 joules per gram. And then something with a really, really low latent heat that I looked up is paraffin wax. And you can probably test this yourself. It might not be exactly 100% paraffin wax, but if you have ever taken a candle before and dipped your finger in the wax, you know that the wax is really, really hot, right? But like when your finger comes into contact with it, it just doesn't really have a lot of heat capacity, so it doesn't really burn you that much. So the latent heat here is 1,765. Oh, sorry. Oh, no. 176 joules per gram. I was like, damn, what am I talking about? All right. Last topic, and one which I did not necessarily assign a homework problem on because it's happening here right at the end, and I don't really think it's necessarily all that important for a lot of the stuff that we're going to do moving forward, but you should at least hear it, is the notion of enthalpy. And enthalpy can be kind of a confusing concept to a lot of people. I mean, you've probably heard it sometimes before, and I'm not sure if you have a good conception of what it actually means. Well, enthalpy is just another state variable. It's just something that determines the state of a system. And we define it as the internal energy plus the pressure times the volume. And the whole point of, instead of defining the system by the energy, but adding on this bit right here, is because it actually, in practice, we don't live in a vacuum, right? So if you want to make something, if you want to create an atom in a tank of gas, you actually need to move the gas out of the way of the particle first. And so this PV right here just tells you how much work you have to do in moving the air out of the way in order to actually put a particle there, in order to put energy there. So that's the point of enthalpy. So now I'll just show quickly why it's actually convenient. So let's suppose we take V to V plus delta V. We take U to U plus delta U. And we take H to H plus delta H. All right, let's write this all out. Okay, H plus delta H by definition is U plus PV. Now, if we expand out all of these things, we've got U plus delta U plus P times V plus delta V. Do a little rewriting here. So we'll group this into U plus PV. That's just the original enthalpy. Plus delta U plus P delta V. We're almost done. I feel like I can see some people getting a little bored. This is just H right here. Delta U plus P delta V. Yeah, and this is... So all this is telling us is that we can cancel out H there, and the change in enthalpy is equal to delta U plus P delta V. So now let's use the first law of thermodynamics. Delta U equals Q plus W, which is equal to Q plus minus P delta V, because we're always talking about quasi-static compression, plus whatever other kind of work you're doing. Maybe you're doing some work that isn't compression work. Who knows what it is, but it's something other than quasi-static compression. So if you do have other kinds of work being done, then the enthalpy, the change in enthalpy, allows you to nicely just forget about this compression term right here, which is accounting for you having to move some substance out of the way in order to put like a particle into a gas tank. So let's watch this. So it's just going to be Q minus P delta V plus W other plus P delta V. And then you see that the P delta V cancels out with the other P delta V. And so the change in enthalpy is only sensitive to the heat added plus the work done by other things that don't include the compression and expansion. So if you are somebody, if you're like a chemist or something, and you don't want to constantly be tracking by hand this this piece of work that's necessary in order to put particles into something and take them out, you're going to pretty commonly use enthalpy because it just builds it in on its own as a state variable. And so that's why it's so widely used in chemistry. Okay, so that ends all of the content that we had to cover for chapter 1. And next week we will get through chapter 3, which is going to deal with kind of like the second law of thermodynamics, talking about microstate counting and whatnot. So that'll hopefully be when it gets a little bit more fun.